Okay, you know, Mr. Bergman, that was pretty good.
Well, you finally like an instrument
Yeah,
that I play?
that was pretty amazing. You know, let's try it again. But this time...
Well, this is my new instrument. It's called well, it's the cowbell.
Yeah, I know, and let's try it again. But I think this time I could use a little more cowbell.
You want more cowbell?
I think a little more cowbell ought to do it. You know, and just really explore the studio space this time. Just get out there and do your cowbell thing. All right, let's try this again. All right. You're gonna want a little more cowbell on that track. Okay, I gotta have more cowbell.
Got more cowbell.
All right. Beautiful, absolutely beautiful.
Oh, I know. You know, not
is,
too many songs feature the cowbell.
You know, that's true. They don't a lot of them.
I would probably be doing a disservice for every member of the cowbell land.
Yeah.
Because, you know, if you got a job where the cowbell is featured, then you should play it.
You got to do it. You got to do it. That's nice. That's great.
That is really good.
Yeah, that's nice. I liked it a lot. You might want to stick with the cowbell.
So maybe I should give up my day job.
It's entirely possible. Chemistry may not be the thing for you. Cowbell playing. To songs by the Blue Oyster Cult, maybe your calling.
The cowbell.
Yeah, that's nice.
Yeah,
very nice.
Yeah, the Blue Oyster Cult. You know, they're kind of like a group. I was alive and old enough to know who they were.
Yeah, and I heard them on the classic radio stations.
That's amazing.
That was nice. Very good.
Yeah, today we want to talk about how to predict redox reactions. Oh my, yeah, this is one of those hard ones. Yes, indeed. And so we should probably do that right now.
Yep.
All right. So if you turn in your packet, right now it's page 17, but it might look on different pages, so let's not overthink this here.
Yep.
Because the pages could change over the years, but right now it's on page 17. Essentially, we have simple oxidation reduction. The abbreviation, by the way, is called redox reaction. It stands for oxidation reduction. And this single displacement reaction, or we call hydrogen displacement, you see the calcium is going to jump into the water, and it kicks out the hydrogen. It's actually better to think of the water as HOH here. And as that works out, the Ca gets with the OH. The key thing I understand in terms of this being a redox reaction is the calcium has a charge of 0, and here is a charge of +2. So that charge is going up, the up-down thing. And the hydrogen is a +1, and he's dropping down to 0. The oxygen is staying from -2 and -2, so there's no change. Remember that, 1 up and 1 down. You see, the trick on this thing, guys, is that you're looking for one chemical to go up in charge, oxidation, and one chemical to go down in charge, reduction.
Right, so one to get more positive, one to get more negative.
And so these examples are examples you've probably seen. This right here is an example of another single replacement reaction. You've heard of those before. The zinc is replacing here the copper in the reaction, and that's what occurs. Now, we had this thing called the activity series last year, but the good news in APChem land is that we don't need to get too worried about that, because if they give you a reaction, it always occurs.
Yep.
So the idea of no reaction, you don't need to worry about that, because at least for what we're training you for a particular question on the exam, there is no reactions, so you don't have to worry about that. Halogen displacement, this is one you may not have seen, but the chlorine, which has a 0 charge, can become a chloride with a -1 charge, and then we have the bromine with a -1 charge going to the bromide, pardon me, going to the bromine with a 0 charge. This should probably be over here.
Yeah, and one thing you also might want to point out, Mr. Bergman, is that with the KBr and the KCl, since those are aqueous solutions, on the AP test, again, if things dissociate in water, we have to split them up and cancel any spectator ions. They always want the net ionic equation.
Yeah, this would be Cl2 plus K positive plus Br minus goes to K positive plus Cl minus. And I'm not balancing it here, folks. We'll make sure we do if we do the. We just want to show you the different options.
Yeah, and then the K's would cancel in that case.
The K's would probably cancel, and we'd worry about that later.
Yep.
We'll do some examples, but just want to show you some examples.
Right.
And there's the disportionation reaction. If you recall, we did an example like that.
I think that was the exact same problem, if I'm not mistaken.
The exact same reaction where the chlorine is going to the hypochlorite, and it's going to the chloride, so it's going both up and down, oxidizing and reducing.
Yep.
So we just want to highlight those. The important stuff you'll see here.
A lot of these are wrapping around. Our text kind of got jumbled in our
I don't know what happened
here.
I must have changed fonts a little bit. It must have messed everything up.
Yeah, sorry about that.
Again, this is actually, let's just jump to this screen. This is the key screen to understand.
Yep, this one and the next screen.
The next 2 screens, it's probably all on one page for you guys.
Yep, this is page 18 if you're current
This is something I must hate to tell you, but it must be
memorized.
memorized.
Yep.
Because you're going to have a point where I'm going to say this plus this makes what. And when I do that, that means that if you have an oxidation reduction reactions, you must memorize that permanganate in an acidic solution turns into Mn2 positive. I recommend that you put these on note cards.
Yes.
I don't know how else you're going to memorize this.
Yep.
And then permanganate in a basic solution turns into manganese dioxide.
Yeah.
And then manganese dioxide in an acidic solution turns into Mn2 positive, and etc. Dichromate does something, chromate, nitric acid. Actually, here's an important point here. Remember we said nitric acid or nitrates hardly ever do anything. That is correct, except in this instance. Nitric acid will often turns into nitrogen dioxide or nitrogen monoxide, depending on whether the solution is dilute or concentrated. And then we have other things. Metallic. We should actually talk about when I say metallic. What does that mean, Mr. Sams?
Metallic ions are ions that come from a metal.
But how does that relate to metallus?
Oh, metallus. Sorry, I didn't see that. Okay, metallic is going to be a transition metal that has the highest charge, so like iron 3. And then metallus would be the one with the lower charge. So in the case of iron would be +2.
Another example might be C10, positive 4. And it goes to 10, positive 2.
Right.
And so at some point, people in chemistry land, you need to have memorized the common charges of these metals. Our students memorized it on the memory table. And then free halogens, what's that mean, a free halogen?
Free halogen is just going to be like Cl2 or I2 or Br2. Those are the ones you're going to encounter.
And they change the halide, so that turns into chloride, or iodide.
Right.
Or bromide and bromine and bromide. And this is sodium peroxide. It can turn into hydroxide.
Yep.
And then hydrogen peroxide can turn into oxygen. Now notice that these are important oxidizers. So these are things that reduce. And if they reduce, they are things whose charges go down. Conversely, we can look. So this is actually, let me do something else on that table. I would say on this table, this is the down table. The table where the charges go down.
Right.
And then the second table that you have.
This is the up table.
This is the up table. And then halides can become halogens.
Yes.
Free metals can become metal ions. A free metal would just like be iron.
Right.
And then it becomes a metal ion like Fe+2.
One thing you'll notice that doesn't show up on this chart is you don't have these metal ions becoming free metals if they're transition metals. They're generally
very rare.
Yeah, very rare.
Metallus, so like say copper +1 can become copper +2. This is the cuprous atom, hence the OUS, and the metallic atom, or the cupric atom, is how that is. Sulfite, watch this one, can become sulfate. And then, now here's a tricky one. We have halogens in both of them, but if you have a free halogen, and if it's a dilute basic solution or a concentrated basic solution, it can become the hypohalite ion or the halate ion. So this means in this particular example that the Cl2 can turn into the ClO negative if it's a basic solution and it's dilute.
Right, so chlorine goes to hypochlorite. That's the hypohalite. It's the chlor is the prefix we're using there.
Yes, the chlor, yes, exactly. And if it's concentrated, it will become the chlor 8 ion, which is ClO3 negative. Okay, so these things need to be memorized. There is just no better way to do this.
Mr. Bergman, I actually see an error on our slide there. It's correct on the handouts, but instead of Cr2O4, that should be C2O4 for making carbon dioxide.
Oh, yeah.
So that should be just carbon, not chromium.
There you go.
A little typo.
That is oxalate turning into carbon dioxide. Good call. The handout's correct, and the podcast is wrong. So we're going to just walk through some examples like this, and then you're just going to have to do them a lot. Okay, so if I have solid copper, all right, solid copper, so that means that Cu with no charge is added to dilute nitric acid. So I'm going to say nitric acid. Now I'd still, because nitric acid is a
strong acid,
I must dissociate it.
Right, dissociated. Either side of the equation, AP test people want it dissociated.
And now I need to figure out what it's going to turn into. Now I know it's going to be a redox reaction since this is a redox reaction podcast. But also, if you see a pure element, it's got to change its charge.
Yes.
And so here's a charge of 0, so it must now go to a higher charge. Now there are two charges that copper can attain, 1 and 2. Copper 1 or copper 2.
Yes.
Frankly, they don't really care what you do, but copper typically likes to go to the 2 charge.
Yes.
So this will be Cu2 positive. So now we've defined who is going to go up. Now we need to find somebody to go down. Now this is a little tricky because the hydrogen right here is +1, and he could drop to hydrogen gas, which is a 0 charge.
Good.
But this is a dilute nitric acid.
And that's one on our down list.
If we go back to the down list, if we have dilute nitric acid right here, it turns into nitrogen monoxide, or NO. So the other product is NO. And that is kind of your skeleton reaction.
Right.
But it's not balanced.
No, because remember in the last...
balancing the equations. And so when they balance the reactions, of course, it's the half reaction.
Yes, just like we learned in the last podcast, balancing the half reaction
I'm going to try and do these relatively quickly.
Yeah, we're not going to just talk through every single step.
The nitrate is turning into nitrogen monoxide. So now I'm going to have to say 2 waters on this side because I need to balance my O's. Then I'm going to put 4 hydrogens on this side to balance my H's. Oh, and I did the electrons. The charge, I need to do 3.
3.
I'll need 3 electrons on this side. This needs to be multiplied by 3. This by 2 because the lowest common multiple is 6 electrons. Let me change colors here. So that's 3, 3, 6. 6,
8,
8, 2, 2, and 4. So when I bring everything down, the electrons cancel. I'll have 3 coppers plus 8 hydrogens plus 2 nitrates makes 3 Cu2 positive plus 2 nitrogen monoxides and 4 waters.
There you go.
So these problems, I'm afraid, are long and cumbersome. All right, a solution of potassium permanganate. All right, solution. When you see the word solution, what do you do, Mr. Sam?
Dissociate.
And besides, it is a potassium compound.
Yep.
And it's a NaCl, so it's a NaT. It's always soluble. So I'm going to write K positive plus permanganate. Now, permanganate has a couple of rules. If you ever see permanganate, in fact, you should think that it's a
redox.
Redox.
Almost always, yeah.
And it's mixed with an alkaline. We'll talk about that in a minute. Solution of sodium sulfite. Sodium, of course, is a NaB by definition. So that's sodium and then sulfite, SO3, 2 minus. And an alkaline solution, what does that word mean, Mr.
Alkaline means it's a basic solution. So not an acidic solution, so we're going to have to balance this using the base balancing rules.
So we have something to go up and down. Well, you've got permanganate, so if we go back to our chart, permanganate in a basic solution, here is basic solution permanganate, it goes to MnO2. So this goes to MnO2. Plus, now we have to look for something because that's a down.
On the up list,
this
sulfite.
Is the down.
Yep.
Now, potassium has a +1 charge. For it to go up, it would go to +2 or +3. You ever heard of potassium +2?
No, never.
I haven't either. And the same thing with the sodium.
Yeah, not going to happen.
So the sulfite, though.
Sulfite, that's on our up list. It can make sulfate.
The up list. So if we look at the, oops, that's not the up list. If we look at the up list, we have sulfite and sulfate somewhere. Here they are. Sulfite can turn into sulfate. These are going to be eventually memorized by you, but we don't expect you to do that. So the other object is sulfate. So this is like your skeleton reaction. The potassium and the sodium will drop off. So I'm going to write it like this. I'm going to say MnO4 negative plus SO3, 2 negative, is going to turn into SO4, 2 negative, plus MnO2. Now what you would need to do is balance them. I'm just going to set these up. I'm not going to do this. So the sulfite turns into sulfate. And then you need to balance this using basic rules.
Yes, so any of the hydrogen ions, again, you have to cancel those out with hydroxide ions on both sides of the equation.
And this would be the skeleton or the beginning of the permanganate to manganese dioxide. I'm not going to write out the whole thing because it would take too much time.
And we learned how to do that last time.
And we learned how to do this in a previous podcast. So you would then do all the balancing stuff on both sides and solve the problem. But the hard part is getting it all to knowing what the products are. Once you do that, the procedure is relatively easy.
Right.
Now, ethanol is completely burned. When you see burned, this is actually an old type of reaction we used to call a
combustion reaction.
Combustion reaction. Now, combustion reactions are easy. They happen to be oxidation reduction reactions.
They're very simple.
These are the CH or the CHO reactions. When you react them with oxygen, when they burn something in air, you're always reacting with oxygen. It always turns in the exact same two products.
CO2 and H2O every single time.
Now, the beauty of this particular reaction on the AP test, just as a side note, is the way that this is scored is they always scored 2 points for the products and 1 point for the reactants. So even if you do not know the correct formula of ethanol, then you would get
Still 2 points.
But it does require it to be balanced, so you might just make some things up here.
Yeah.
All right. Turns out, I like to ethanol. There's this prefix in this is called an organic compound.
And we'll talk about that later.
Yeah, we will. But real quick, I want to just give you a real mnemonic device. Is that what you call it?
Mnemonic.
Mnemonic. My elephant plays basketball. Did you know that?
No, I did not.
Yeah, it's kind of like I'm a good, cowbell player.
Yeah.
Yeah. This stands for methyl. methyl. This is ethyl. This is propyl. And this is butyl. This actually, the prefix tells you what about the compound?
It tells us how many carbons are in the compound.
So in terms of this would be 1 carbon, ethyl is 2 carbons, propyl is 3, and butyl is 4. So if I want to write ethanol, how many carbons will ethanol
That's
have?
going to be 2 carbons.
So it's got 2 carbons, and then what it has, if it's an alcohol, the all ending is OH. And actually you just fill in the rest of these
H's
with hydrogens. Now, actually, on the AP test, it would be totally acceptable to write it in a stick figure structural formula as I just did. Plus O2 makes CO2 and H2O. Now, you may not completely know this, and then we'd have to go back and balance it, so I'm not going to worry about that. I bet you could balance this real quickly. But that's how it's essentially done.
Right.
So, okay. Now, what about sodium metal? This is cool. Remember we did this a couple of years ago for mold day, didn't we?
Oh, yeah, we did.
I think we used potassium.
We tried to use potassium. That was kind of a dud.
Well.
No,
yeah, but sodium
worked pretty well.
Yeah.
This was fun.
I had a friend, I don't know if I should tell you the story, but he dropped my old high school, that's who it was, my old high school chemistry teacher, they got a hold of a bunch of sodium, they wrapped it in a plastic bag, dropped it into a lake, and ran. Every fish in the lake.
I can imagine.
Died.
By the way, that's illegal,
yes,
so don't do that.
Never try that at home. She didn't get caught. Okay, sodium metal. So this is a Na, so I should just...
there's no charge on sodium metal.
Okay, so this is just pure
sodium. Oxidation state of 0.
Water. Now, when I add it to water, I oftentimes like to
Let's go HOH.
HOH.
Yeah.
Now, the sodium has no charge, so he has to acquire a charge. The only other charge you've ever learned about is...
Na+.
So +1, Na+1.
Yep.
So that's going up.
Yep.
This is our upper guy. Upper? That sounds like we're taking drugs or something.
No.
Okay, we need to find somebody to go down. The hydrogen here is a +1. The O is -2, and this hydrogen is +1. So let's talk about O for a moment. It's at -2, so if we're to go down, I have to go down to like -3 or -4.
Not going to happen.
Not going to happen. But the H is +1, so we can go down to...
H2.
To 0 charge. Or
right,
H2.
0 charge.
Now, what does that leave us with?
Looks like we got some OHs left over there.
That leaves us with OH.
Yep. Now, this is one of the metal displacement ones we talked about earlier.
Yeah, just as a note, you might think of it as NaOH plus hydrogen, actually. But the NaOH, of course, is a Na, and so it completely dissociates.
Completely dissociated, so we're going to write it as the ions.
Separate the Nas and the OHs. I don't believe that's balanced. We probably could balance this one.
Yeah, not balanced.
I need to put a
2 there, and then a 2 in front of hydroxide, and you're good.
And a 2 here, and I think we're good, yeah. All right, I think we just have one more, and then we can call this a podcast. All right, hydrogen, and folks, just as a side note, we're doing like 5 or 6 examples, but the problem is that that doesn't suffice. You have to just do these with us.
Yes, lots and lots.
You probably got to do 50 of these. I mean, I hate to say that, but that's really what's going to help you figure this out. All right, if I got hydrogen peroxide solution, now it says solution, but you'd think you'd dissociate it, but hydrogen peroxide stays together, so it's just H2O2. Now, as a side note, what is the charge or the oxidation number of O in peroxide?
That one is -1.
Yeah, okay, so that means he doesn't like that.
No.
It's not very common. And that reacts with iron 2 sulfite, so that Fe2 positive plus sulfate, which is SO4, 2 negative. So we've got to find charges that can change.
Yeah, well, I'm guessing that oxygen's going to change because it doesn't like to be -1.
So what is he going to turn to?
Well,
oxygen has a couple of choices. He can go to -2, or he can go down to 0.
Right, and
actually, up to 0 or down to -2. I said.
Right, and on our list it says H2O2 becomes O2.
So that's going up or down?
That one is going up, but strangely it's on our down list.
Or do we have a typo?
I'm not sure.
-1 to 0 is an up. You know, on our, guess what, guys? We're going to have to fix this. So if we go back to our down list, this should say water. And then if we go to our up list, we need to fix this on our...
Yeah, we'll fix it on our handouts.
Unfortunately. H2O2 can go to O2 on the up list.
There you go.
That is the correct way that this is done. So let's go back to our screen. That's the wrong screen.
Yep. Okay.
All right. So now.
Now, since we don't know what oxygen's going to do, let's look at iron, our other choice over here.
Now, iron's that's the ferrous.
That's the
lower one. So he actually could go up to +3 or down to 0.
Right, and it's pretty rare for them to go down to 0.
Yes,
and if we look on our up list, metallous ions go to metallic
so
ions.
we can go to Fe3 positive.
Right. So since that one is going up, we can assume then that the oxygen is going to go down.
Now, when oxygen goes down, you don't write O negative 2. In fact, oxide does not exist in nature by itself.
No, it's always with something.
And so what's the other something that's around? We have sulfate and we have hydrogen.
I would stick it with hydrogen.
If you have hydrogens, that essentially makes
water.
So our two reactants, I think we probably should balance this one. This
yeah,
would be
probably.
good to balance. Let's take a look.
Now, notice that sulfate's not going to do anything. Sulfate is not on our list as...
it could go down to sulfite, actually.
It could, but that's probably not going to happen too often.
And again, this is one of those things that if you did that, it probably wouldn't kill you on that for the AP test. But
you got your charge wrong. Charge is wrong there.
I've got them backwards, don't I?
Yep.
This is going from 2 positive to 3 positive.
There you go.
I'm going to add 1 electron. So that's the first half reaction. That's the easy one.
Yep.
And now I'm going to do H2O2, and that goes to water. And it's in a solution. It doesn't say if it's acidic or basic, so we assume it's...
I'm going to assume it's acidic.
Assume it's acidic. Now
yep.
we've got a problem with the water, so if
yep.
I put 2 waters right here.
Mm-hmm.
Now
we
I
have
have
a
to
hydrogen
balance
issue.
hydrogens, 2 hydrogens, I believe I did.
Yep.
And then I'm going to have 2 electrons on this side, and that's it. Actually, I do need to multiply this side of the top half reaction by 2,
yep.
and that's it. So then this becomes, I'll double that, 2, 2, and 2. My electrons cancel. I end up with 2H positive plus H2O2. Notice I've ignored the sulfate. We talked about that a minute ago. Plus Fe, 2Fe, 2 positive, makes 2Fe, 3 positive, plus 2 waters. And so that's how we do that.
It is. You know, Mr. Bergman, guess what?
What?
I got a fever.
You got a fever.
And the only prescription is more cowbell. Oh, he smacked his head. More cowbell! More cowbell! Push through the pain!